All right. Hey everyone. This is the mid-project update for KCP. My name is Mayer-Patel and I am being advised by Professor Ketan Mayer-Patel. Let's quickly remember what KCP is. It is a modification to TCP whose goal is to improve on the fairness of TCP. TCP currently transmits C-wind worth of data every RTT, and the C-wind or congestion window adjusts based on the network congestion. So you have a fixed packet size and a varying frequency. If you want to send more data or increase your throughput in TCP, then you send more of these fixed size packets. In contrast, KCP transmits a segment every millisecond. The size of the segment adjusts based on network congestion, and we have a fixed frequency in this case, namely 1 millisecond. How does this benefit fairness? Well, a very well-known problem with TCP is that flows with shorter RTTs have an advantage over flows with longer RTTs. But we expect that this advantage will not be present with KCP. We expect that larger packets will be preferentially dropped. In terms of our methodology, at the moment we are considering two different traffic models. We have infinite sources and we have a Poisson distribution traffic model. We're starting with a simple model of fairness right now, namely we count the number of bytes through a bottleneck for each TCP flow for every second. So every second time slice, count the number of bytes for each flow. And you can determine the average for every time slice across the flows, and you can also determine the standard deviation. A lower standard deviation for each time slice indicates that each node gets a more equal amount of throughput, which we are taking as to mean that that is more fair. For our experiments, we are using NS3, which is a discrete event network simulator. We have implemented KCP in NS3, and we are now going to run experiments with different workloads and topologies and different traffic models. We plan to benchmark NS3's default configuration of TCP against our own implementation of KCP. We've implemented KCP as a drop-in replacement for TCP. We created corresponding classes, namely KCP Socket Base, KCP Factory, and KCP L4 Protocol. These names may sound familiar if you've been using NS3, and they should work right in the place of TCP. There is a slight hiccup or implementation detail here in that KCP and TCP sockets both cannot run on the same node at the same time. This is a minor issue. It's only due to the tools we're using, namely TCP dump and TCP trace, and it can be easily overcome by simply assigning KCP a protocol number. We've also created some data collection, data processing, and plotting infrastructure that streamlines collecting data, running simulations, and processing everything. We're using a standard dumbbell topology in our simulations. I've superimposed a few of the characteristics of our dumbbell, or properties, onto this image. Namely, the bottleneck link is 1 megabyte per second, and the leaves or the last mile links are 100 megabytes per second. All of these sources are on one side of the bottleneck, and all of these sinks are on the other side. And some final details. Each of these infinite sources that we're talking about, we'll talk about the infinite sources first. They all start randomly at some time in the interval 0 to 5 seconds. And these 0 to 5 seconds are simulation seconds. This simulation runs for 60 seconds in total, and we will ignore the first 10 seconds. So we ignore the first 5, which is the startup time, and then the next 5, all the flows should be running, but we want to ignore that because that is potentially noise. All right, we are now ready to talk about some preliminary results. Let's take a look at our first example of an infinite source and a single flow. There's a single sender, a single receiver, so there's one flow. Of course, since there's one flow, that would imply that the standard deviation of throughput is 0, so we will not plot that here. But what we do have plotted is the throughput versus time for 2 different simulations, one simulation that ran a TCP flow, another simulation that ran a KCP flow. We see that TCP is fairly consistent at about 1,000,000 bytes per second, but KCP lags behind. It's slightly slower at 925,000 bytes per second, just eyeballing this graph. While this may seem concerning at first glance, it is an unrealistic scenario. Why? Well, how many times do you have a bottleneck link where there's only a single flow for a long period of time that is occupying that link completely on the internet? This is unlikely, so we are not too concerned about this scenario. So let's move on to the next one. Let's move on to a little bit more of a realistic scenario. We now have 125 flows, and one side of the bottleneck has 5 senders, the other side has 5 receivers, and there are 5 flows between each sender-receiver pair. So that means we have 125 flows. And of course, because this is throughput, higher is better. And we see that TCP is again able to fully utilize the bottleneck, and KCP does a pretty good job as well. We see this large variation graphically, but if you notice, the peak for KCP is at 8,000 as well, but the trough of this plot is just 50 bytes per second below at 7,950. So KCP appears to be doing a pretty darn good job in this case in terms of saturating the bottleneck. But what about the standard deviation measure that we're using for fairness? So we have plotted the standard deviation for the same case, and we see in this case, with this configuration of our topology, network topology, we see that KCP's fairness is significantly better than TCP's. In fact, in the latter portions of this simulation, around 30 seconds and later, we see that the average standard deviation of throughput is approximately, if we're eyeballing this graph, about 15,000 bytes per second, whereas the average standard deviation of throughput for TCP is approximately 30,000 bytes per second. So KCP is doing 2 times better than TCP in this particular case. Next, we will be using a Poisson distribution. This part is a work in progress. I'm currently implementing the scripts and configuring a topology to get this to work. The implementation is ongoing and the testing will occur soon. So far I have been able to consistently meet the target milestones we've set loosely. The last milestone was to implement a more realistic traffic model. That was the Poisson distribution model. The original goal was to also include varying RTTs, but we will do that at a later point. There's a little bit of slack in the schedule I had proposed, so we should be able to complete the more realistic traffic model and also do the benchmarking with these new models before the next deadline, which is November the 2nd. This concludes my presentation. I look forward to hearing everyone's feedback and questions, and I am looking forward to also seeing your presentations. Thank you.